Good. It moved to a different folder for some reason. All right, so let me get this up and see if you guys can see it real quick.
Okay. Welcome, everyone. Randy Thompson is joining us from GoDaddy. Talk about Tiamat deployments. This is going to be great. Thank you, Randy, for being here.
No problem. Apologies that I wasn't able to make it the other week. All right.
Life happens.
Yep. All right. So this presentation is effectively about Tiamat and how we utilize it here at GoDaddy. So we're going to go ahead and just go ahead and get into it. Okay. So the topics that we'll cover in this is basically an introduction of myself and GoDaddy. The Mayhem heterogeneous environment. Effectively, what we'll step through there is the issue that we encountered within GoDaddy with everyone having separate environments, Python installs, versions, various pip dependencies, and requirements on versions for those, and kind of how we solve for that with Tiamat. The create once, deploy everywhere. There we'll be actually walking through the reasoning on how we solved for it, and basically explain how Tiamat does solve for that. Oops, sorry. Then basically what we'll go through is kind of the flow of our build system now with Tiamat versus the old system, and how to use it, as well as upcoming features. So introduction, who am I and where do I work? All right, well, again, hello, my name is Randy Thompson. I have worked in the industry for about 16 years now. I'm a father of 3, 2 boys and a girl, and I work remotely in Iowa. I've worked in various places throughout the Army in the Signal Ops, which would basically be IT for the Army, various positions for IBM, such as Unix system administrator for their AIX systems, Windows administrator, and then a system security admin as well. For GoDaddy, I've actually held several positions over the year as well. GoDaddy being the longest tenure I've had of nearly 10 years, June this year. I've held positions there as a sysadmin, as a SRE, and SDE now. Currently, I am a senior SDE with them. Some of my hobbies are functional programming, performant code, and distributed systems, which include Erlang and Elixir and Rust. All right. So GoDaddy was founded about 1997. GoDaddy provides an array of services such as domain registration, hosting, websites, website builders, email, SSL certificates, and many more. I actually work in the domain side of the company, where we primarily focus on domain search, domain registration and renewal, and any add-ons that they have. We have offices in various locations all around the world and the US. Unfortunately, currently they're closed due to COVID-19. We're hoping to get back in there soon. Okay, so Mayhem, heterogeneous environments. All right, so next I'll describe our environment and the problems and traditional Salt installs presented while rolling out our Salt Stack services to consumers. All right, so the domains org here at GoDaddy has roughly around 2,600 hosts. They come in a mix of platforms and operating systems and versions like physical and virtual machines, containers, CentOS 6 through 8, Windows Server 2012 through 2016, core and standard. And we are currently moving things into AWS. So as many of you know, these operating systems have different Python versions either installed by default or available for them. CentOS 6, for instance, the latest version they typically have available without reaching outside for third-party repos is 3.4, I believe. and then 2.7.11, I think, for Python 2, which Salt no longer supports. And then, outside of compiling the version yourself, of course, which we do sometimes. So as well, those environments also have various package systems for installing things as well. So it's kind of a hodgepodge of stuff, and it's a pretty big mess. One of the biggest issues we had, of course, is just trying to compile Python from source, Python 3.8 actually, and then providing that throughout our environments. We ran into a lot of problems with, say, glibc, where you could build the binary on CentOS 6 and then install it on CentOS 7 and CentOS 8. However, you'd run into issues where, okay, you have a binary that works forward with CentOS 7 and CentOS 8. However, you've now taken all of the CVEs and bugs that have released since that glibc version for CentOS 6 into your CentOS 7 and 8 environments, and that's a big no-no from a security standpoint. And you can't really build up and go down because that's not how glibc works. So it created a huge issue. On top of that, some teams were already using Python, and they had services built in it or applications built in it, and they required specific versions of Python, or they had pip dependencies that were installed that required specific versions as well. And we didn't want to really mess with those environments because anytime we'd come in there and apply a hammer for installing something would potentially break that app or service, and that's a big no-no as well. So a lot of this was a big deal because we couldn't really get in with those teams and work with them to try to uplift their environments into something more modern, whether that be a new operating or a newer version of their operating system like CentOS 7 instead of CentOS 6, or say moving from Python 2.7 to 3.8 or 3.6 and above. Because they simply didn't have a lot of time. They're loaded down with feature work or firefighting or making meetings about nailing down some specific new feature they wanted to get out, or specific functionality in their application. So it's very difficult to work with our developer teams to figure out how we can move them somewhere else that is more beneficial for our tooling to help them maintain things like patch compliance and give them tooling for spinning up entire environments where their servers are already configured out of the box. So in such environments and situations, it becomes difficult to account for all possible scenarios in which we may land the services we provide with SaltStack, meaning basically that because of this largely separate environment, we couldn't just have a deploy and run strategy that worked out of the box for everybody. And these were servers as well, that where you'd have servers in the same cluster running the same applications, and even they were completely different between each server in terms of what was installed and what version was. So kind of a nightmare situation for our engineering team to roll out our services to them. So with conventional means, it is possible to set up SaltStack to work within this environment, but it would require an immense knowledge of everyone's systems and applications, which we just don't have, and we simply don't have the time to learn. So, basically we have this huge, large heterogeneous environment that belongs to several different teams, where in some cases a single host could actually have applications installed to it from separate teams, all on the same host, or spread out across various DCs or various networks and cloud providers, etc. And like I said, we just didn't have the time to gather all the data on everything out there in order to try to make this work via conventional means of Salt, where you'd break things out via, grains or some other means of identifying everything, and then running the correct commands to facilitate our services. And even if we could, the amount of variation incurred from that would be less than ideal as well. You're talking about a massive hodgepodge worth of salt code to just facilitate something like that. And that's not an ideal situation to be in, because once you have this huge repo or multiple repos worth of various states, pillars, reactors, orchestration states, etc., it becomes really unwieldy and really hard to maintain. So it's kind of less than ideal situation either way there. The amount of things that can go wrong in such an environment are difficult to enumerate, but luckily not all hope is lost. So create once, deploy everywhere, or the power of built Python binaries. So next we'll be talking about how Tiamat kind of solved our problems with this heterogeneous environment. So after the initial discovery, we did it on our environment and found out that this was just basically a nightmare scenario for us to try to solve for. We decided that perhaps it would be better to provide a binary of salt stack to our consumers. Ideally, this binary would be used to drive our services for automated patch management and greenfield project creation. Initially, I looked at things like PyOxidizer, Nutka, if I'm pronouncing that right, and SaltBin actually, which is a archive project now, I believe, at this point. After asking around and speaking with Wayne, actually, I was turned on to Tiamat, and this project basically hit all of our goals. So, we wanted to provide a consistent environment for SaltStack to run in. We didn't want to require any additional system or pip dependencies that were, out of the normal, that would normally be installed on a box. We definitely wanted to provide extensibility so that people would have the ability to effectively change things within this binary or the things that this binary ran, and the ability to run across all of our supported platforms and distros in our environments. And that's a pretty tall list to live up to, but Tiamat had all of them, luckily. So what is Tiamat? Oops, sorry. What is Tiamat? Tiamat is the single binary builder for Python projects. So its goal is basically to simplify the process of building Python projects as a single frozen binary. It is configurable, extensible, and its development cycle is fast-paced. I know sometimes it can be sort of frustrating with other projects that are open source where, development moves quickly and PRs get put in, but acceptance of those PRs is sometimes rather slow. Tiamat moves pretty quickly, where normally if you get something in there, it's either approved or merged within about 24 hours or around so. So it allows us to create self-contained binaries of Python projects like SaltStack with the Python language, system dependencies, and any pip dependencies kind of bundled into this binary. So, like I said, that provides your consistent environment right there. Everything's already contained within that single binary, and it doesn't really require any additional system or pip dependencies outside of what you would normally find, unless you're doing something pretty exotic, in which case you can build a static binary and pull those dependencies in as well. And that allowed us to build something that would work across all of our platforms and distros. Luckily for us right now, we really only support CentOS 6 through CentOS 8, with some, Amazon Linux now coming into the fray. But beyond that, we don't really deploy to things like Ubuntu or say your BSDs outside of, net applications and stuff like that. So when the binary is generated on older systems, it is more likely to be compatible with newer distros. Now, I kind of talked about that before. So glibc works like this effectively. Glibc is backwards compatible. So when newer versions come out, if you built something on an older version of glibc, it should work with that newer version of glibc, right? So like I said, we could build a binary on CentOS 6. And in fact, I did do this during my conference talk, which unfortunately, due to some issues, wasn't able to get uploaded. But if you build on CentOS 6 with an old enough version of glibc, I think it's 2.24 or 3.2 in there, can't remember. I could then take that binary and actually go to Ubuntu 16.04 and run salt, or CentOS 7 and 8 and run salt, or to Ubuntu 2004 and run salt. I had this single binary I could take everywhere. One of the things you have to be concerned about there, like I said, is that if you're taking this binary from an older version, you're also basically making it so that you have to use older dependencies for that older version of glibc as well. So you're kind of inviting a sort of security hole, so to speak, in your newer environments if you build too far back. So that's something you definitely want to be concerned about. And of course, it is fixable if you have the time and knowledge. You could patch out everything on an older system to make sure that you could build forward, or you could try building newer versions of glibc on older systems as well. But then, like I said, you still run into the same issue where, okay, it's newer on this system, but now if I try to move it over to another CentOS 6 box that isn't running that same version of glibc or newer, I can't run this binary anymore. So that's one of the great things about Tiamat, but one of the things you have to also watch out for. The older the system you build on, the more compatible your binary will be. Effectively, as long as the target system you're deploying your binary to is a equal or newer version of glibc, it basically works on any ELF distro. So you have a wide range of distributions you can deploy your services out, or your binary out to. So Tiamat is also capable of making system packages via FPM under the hood. So Tiamat itself actually has multiple ways it will build for you. You can build one dir, which basically just dumps everything from the build into a single directory. And it's really good for things like debug builds, where if you have an issue, you can kind of dig into what it is there easier than, say, if it were in an actual binary. You can build a one file build, and that will build your binaries. And then you could go a step further with that binary and actually make it a static binary entirely if you have, say, any system dependencies that are more exotic and not common across Linux distributions, if you're building on Linux. And it also uses FPM under the hood directly to build things like, say, .deb packages or .rpms if you wanted to go that route as well. So again, this hit all the check marks for us. From there, I engaged with Tyler and Thomas, and have been assisting with driving development for Tiamat forward since. Tiamat has helped reduce the cognitive load and time to deliver for deployments of our services throughout our environment. What was previously driven by Bootstrap scripts, FPM, and the salt stack is now simply a single binary package as an RPM, and kind of flows through our environments from master of masters to syndicate masters down to minions. So now we simply have this binary that is usable across our environments. However, due to security constraints, like I mentioned before, we do build binaries per distro right now, and it's quite easy to support. So here's our old flow for building things. Effectively, we kind of had everything, separated out by concern. So we had our master configs, our syndicate configs, our minion configs, and our master configs and syndicate configs would also include things like Salt API and Salt Cloud configurations. And then our pillars were actually generated on the side entirely, so that they were not stored in a way where they were susceptible to just kind of being picked up and used as a point of attack. They're all actually GPG encrypted. So each one of those would be built into an RPM via FPM, and then uploaded into our internal Yum repo system. And effectively, what would happen there is we'd use a deploy script to kind of land the minion configs and the pillars, as well as configs and states, out onto our minions, and everything else would flow to either our multi-master PKI master of masters or a multi-master PKI syndicate masters, and then also out into our minions. It was quite a mess, and very convoluted, which often led to, unfortunately, some breakage. during some releases. And we ended up moving to a new flow, which is actually a flow we started using within the last couple of months. It was kind of designed in the last couple of months and actually implemented within the last month so that we could get things pushed out properly to our teams. But effectively, Salt is actually built separately from everything else, whereas everything else is basically your Salt states, your pillars, your configurations for master minion, Salt Cloud, Salt API, things like any more or any orchestration states, reactors, custom modules, custom states, stuff like that. Everything was bundled up within there. And effectively how this works is we own a repo called CPP Salt, where our team basically makes any changes we need to the Salt binary. So some of those things would be like ensuring that it is updated to the latest version of Salt so that we're always getting CV fixes in as quickly as possible and deployed. And in fact, we actually have a time to delivery for Salt via our team's CPP Salt package that is about 3 to 4 days faster than the rest of the company. As the rest of the company is using a mirror of upstream Salt stack currently. And as we deploy our services throughout the environment, that will change. But we can get binaries built within less than 30 minutes and deployed out if need be, whereas everything else goes through a promotional process that's really slow, so about a day each minimum. So that's kind of a big deal. We're able to actually pivot and respond to security issues a lot quicker than the rest of the company. But any changes we make are obviously then created on a PR. So we do feature branching, and we PR that branch into master. And as that's actually being created, the branch is created. There'll be a job going off to build a binary for that for the dev environment. And any changes you make to that branch will build a binary for the dev environment. When you create the PR, it actually creates binaries for the test environment, and they're passed through smoke tests, integration tests, unit testing, so forth, to ensure that we don't break existing functionality throughout the environment. It's pretty terrible when you deploy out a binary that doesn't work, or say if you're doing static compiling of your binaries and you do it improperly, it's seg faults. Well, now you've deployed a binary out that has broken Salt for everything, and now no one's stuff works and the automation is broken. It's a pretty bad situation to be in. Luckily, due to this, though, you can pivot really quickly and get that fixed. But when the PR is merged into master, that merge actually kicks off the binaries that are built for prod. And we build our binaries per distro, per environment. So CentOS 6, 7, and 8. And dev test prod environments. We haven't expanded that to anything like staging or anything yet, but it's really easy to add in additional environments into our Jenkins files for those to be built. And we also turn those binaries into an RPM via FPM, and we do the same thing where it's built per distro, per environment. The reason why we went with binaries then packaged up in RPMs is because since our environments are largely just CentOS, RPM is the more acceptable way of deploying changes out to the environment. So once we get our RPMs for everything uploaded into the Yum repos of those built binaries, they are then made available to the multi-master, master of masters, and kind of pushed down through the multi-master PKI syndic masters and out to the minions, so that everything gets an updated version of CPP Salt. And since it's an RPM, it's really easy to do. You just run a Yum update or package update, package install, whichever way you want to do it via Salt. The states, pillars, configs, etc., those are actually never built via Tiamat. So they're just the raw files basically turned into an FPM RPM. And then uploaded into the Yum repo. When people make changes to their repo, which is generated from a template repo that we own as well, effectively every team we onboard into our core provisioning platform and Patchman products that are driven by Salt, they get a single repo clone from a template repo. When they make changes to that repo and they go ahead and merge it or create a PR, that PR is tested, and then once it's merged, It's basically wrapped up into an RPM via FPM and synced up to our internal Yum repos. So when you make changes to that repo, what changes you make actually depends on which packages get built. So if you make a change to something that would apply to the syndicate packages that we build, which would be, your states, your pillars, your config, stuff like that. We have some smart little Git logic we do that determines those files and what they belong to, whether minion or syndicate, and then builds that respective package. If you change something like in the minion config, because that's really one of the few things the minion needs, then it would build the minion package. Of course, if the changes are spread across both, you'd get both. So once they're in the Yum repo as well, like I said, it flows the same way, where it goes, it kind of gets picked up by our multi-master PKI masters and masters, and then pushed down through the syndicate masters and out to the minions the same way via, package.install or package.update or cmd.run yum upgrade or what have you. So this kind of really streamlines the flow for us, and the way we have the split makes it perfect for our consumers. And it creates a good separation of concerns. We could do this all in one thing, but then you have to think about any changes that need to be made to the binary, start kicking off builds for things that necessarily don't need them. And now you're basically incurring changes and then updates throughout your environment kind of unnecessarily. So keeping them separate was basically what we thought would be the better way of handling this. But yeah, like I said, they get that cloned repo from our template repo, and then they can make any changes they need to their configuration, their Salt Cloud configurations, or maybe they want to change the webhook URL for Salt API for some reason. Or instead of using LDAP auth like we currently have implemented, they want to use PAM for some reason. They could make those changes. They could add additional states or change their pillars, what have you. And that's all self-contained within that team's repo. So they're the only ones impacted by that change. That RPM or those RPMs are only generated for that team. And when it's pushed out, it's only installed on their systems. So that really allowed for us to kind of also streamline our onboarding process, because as a part of that onboarding process, not only do they get this repo clone from our template repo, but they also get a set of these multi-master PKI syndicate masters, which are hooked up to our multi-masters, our master of masters. And we really only use our multi-masters for things like checking the health of the environment or for a specific team, or say, for instance, there's some sort of CVE released or package that needs to be updated due to security issues. Typically, we can pivot on that stuff a lot faster than, say, a team can, whose developers are all kind of tied up in whatever various feature work or functionality work that they're doing for whatever products they own, which could be several. So yeah, this works out really well for us. We've already onboarded 2 teams in fully into our services, Patchman and the core provisioning platform, which is effectively a wrapper around Salt Cloud to make things kind of easier on our developers. And we are in the process of rolling them out to the rest of the entire organization now. And hopefully after that, the rest of the company. And it kind of allows us to solve a long-standing problem that our company has had, as well as most companies, which is, how the heck do I automate patching without bringing down my systems, or how do I automate patching in a way where we don't have this kind of cookie cutter setup where I try to apply the same type of way of updating servers to every single team, because that's not going to work. There are some teams who have requirements like they can't have certain C libraries installed. Our DNS team is one such team. They simply some libraries they just will not allow installed in their environments or applications. And some teams, like I said, have various requirements on whatever Python version they're running, or whatever glibc version they're running, or whatever request library they currently have installed. So yeah, this kind of allows us to wrap everything up pretty prettily so that any changes they make to their repo is contained to themselves. But also they've got this binary which contains the entirety of salt stack itself, system dependencies, and pip requirements. And it doesn't impact their systems. We don't have to upgrade their Python version. We don't have to touch their dependencies. Hopefully they're using virtual environments. Unfortunately, sometimes we find out they're modifying system packages, and we have to give them a quick slap on the wrist. But yeah, this just puts everything into a single binary, and that we just have to land that into a location that we specified, which is an opt, and nobody's the wiser. So yeah, let's move on to the next one. So how do I use Tiamat? Simple binary builds. All right, so I'm going to go ahead and stop the slideshow real quick. So Tiamat's pretty easy to use. It's a Python package that you can pip install. I believe at this point they are building binaries of Tiamat as well, that you could use. I don't know if that's public yet, though. Do you know, Sage?
There's the beta ones on Artifactory.
Okay. And those are the ones I'm talking about. Currently, Tiamat is in a kind of beta state. There are a few issues that need to be cleaned up before it can be considered sort of production ready for Salt itself. So the goal being that Salt stack or Salt project, sorry, is producing binaries of Salt themselves to then be installed throughout the various operating systems they support, or systems they support. Right now, there are probably a couple of us out there in the wild who are using Tiamat in such a way. We use it pretty extensively on our team, but Tiamat itself is pretty easy to work with. So you can go to their library here in GitLab, and you can either clone it or you could pip install it. And really, Tiamat only needs a couple of things from you. It needs a configuration file, which basically tells it kind of how to build. It needs a run.py file, which is kind of like your application or your entry point to your application. We have a run.py that we use. Mine's pretty in line with what Salt uses themselves for building Salt and then calling Salt itself. And you need a requirements file basically to tell Tiamat what to build. Now, currently Tiamat is effectively a wrapper around PyInstaller, and it eases the entire process of using PyInstaller. If you haven't used PyInstaller with anything more than a single script, it can get pretty complicated. So this kind of takes all of that out of the equation. They do have some documentation as well. They have some documentation as well. I believe this is on Salt project as well, maybe, or Tiamat.io. I can't remember. But the documentation is available. It's kind of sparse right now, but we're building it out. There will be more added to here, obviously, but it kind of runs you through what you need, and it's basically telling you the same thing I told you. So yeah, I actually make use of Tiamat via containers. So I've actually containerized Tiamat and all of the dependencies that are needed for it and Python 3.6 into each one of these containers. It was a bear to get Python 3.6 working in CentOS 6, but it is possible if you reach for outside repos like IUS. And then we have our FPM container for actually building the RPMs. Now, all of this is actually controlled via a make file, which I can show you right here. Can you guys see this fine?
Yeah.
Okay, good.
Be a little bigger.
I can do that. Better?
Yes, that looks good.
All right. All right, so everything is kind of controlled via this make file I wrote. And effectively, this make file just kind of accepts arguments passed to specific targets within it, if you're familiar with make files, and then builds whatever you specify for that target. So this make file actually controls the building of these images as well as the building of the binary and the RPM. As you can see here, we also have several commands for testing the Docker builds as well. But yeah, the ones we're concerned about here are effectively make binary, where then you then pass it in CentOS 6, CentOS 7, or CentOS 8, and then make RPM and pass in the same things, and it will go ahead and build your binary and then build an RPM of that. And I can actually demo that right now in a way that's pretty quick, as well as go over some logs within our Jenkins master. The reason we're going over the logs instead of actually having it build via Jenkins is because those on average take about 20 minutes for us. The reason being is locally my machine is a solid state drive, and the Docker host that's hooked up to our Jenkins master is actually spinning disks in OpenStack, so it can be somewhat slow. So let's go ahead and oh, sorry, ECS. What's going on? There we go. GHE, and then we want to go into CPP salt, and we'll go ahead and head to the Docker folder. All right, so we've got our make file there, and then we have our various entry points for.
Can you increase your terminal font size a little bit?
Yes, sorry. Better?
Yeah, that works for me.
Okay. So yeah, so these are obviously our Docker files for CentOS 6, CentOS 7, CentOS 8, and then we've got our entry points. So effectively what we do is we turn our Docker instances into basically Dockerized CLIs for each one of these tools. And then we actually use this make file within our Jenkins file to then build these within our Jenkins pipeline. And I'll show the Jenkins file here in a little bit as well. So basically what we want to do here is we want to go ahead and make, and we've gone ahead and made the make file self-descriptive as well. So as you can see here, we want to go ahead and make binary of, we'll say CentOS, I don't know, we'll say 6. Whoa, no. CB into source. Well, that's weird. 1 second. Oh, crap. I forgot to set workspace. My bad. All right. So for binary, we need workspace, and that's provided by us. So we'll say workspace equals home, greater equal, ECS, GHE, salt. And then that should be good. All right. All right, so as you can see here, it's going to go ahead and go through the Tiamat command itself. The stuff that we place in the file for the make file actually is going ahead and doing this for us, where we're doing a log level debug directory source, which is more so for our Jenkins build, but we're providing an actual folder, and then we do the build conf. Yep, and then it starts up, and you can actually see it. It prints out the entire environment for you when you're in debug mode of what's about to happen. And then it will go through and actually install the base packages into a virtual environment that are needed, and then install the dependencies that you have, and then build the binary. So while that's running real fast, what that looks like for a config, if we come over to here and we go to platforms, Linux, build.conf. All right, so in our build.conf file here, we're saying we want to name the binary salts, that the run file is located here, which is a relative path, that the requirements file is located here as well, relative path. We're specifying the PyInstaller version that we want to use. And then we're saying wonder is false. If you set it to true, that will build your wonder installs, which, like I said, dumps everything as files into a single directory. Wonder false builds your binaries. We're forcing locales UTF-8 to true. And And then we're copying in dist utils, and we're setting our timeout for sub-process calls to 600. The default would be 300, so 5 minutes. We ran into issues with our Jenkins master and our Docker slave because they're spinning disk and everything takes so much longer, where 5 minutes wasn't enough time. And you can actually see all of the options provided if you download Tiamat and you run a -- help on it, or if you want to download the code, you can come into Tiamat and you can look at the conf.py folder or file. And this lists out all of the CLI options as well as the configuration options. And most of the CLI options are basically just a copy of these. And these will list your defaults as well as the help. So either install the package, do a -- help, or come look at this file and you figure out what's available to you. So as you can see, it went through and actually started installing everything from our requirements file here. It's downloading everything and converting it into a wheel if it's not already a wheel, and then installing it into that virtual environment that was created on our behalf within Tiamat for the build from PyInstaller. And then next, it's actually going to execute the build against this spec file, which gets dropped into the root of your project by Tiamat and PyInstaller. If we want, we can actually go ahead. No, sorry. We can go ahead and see what was in that requirements file. All right. So right now, because I'm not actually applying my patches to anything, we're installing this requirements file here. And it basically is generated from the SaltStack repo using the pip compile command. You can find instructions for this within the SaltStack repo as well. So I generated it against the specific version of Python we're building, and then we install, a Salt we're building, and then we also install Salt as a dependency right now. Obviously, you can install Salt via providing the Salt folder and pointing at that folder for your source, and it would build from that folder as well. So in case you wanted to do things like apply specific patches to the Salt code itself, like this one for fixing DNF for CentOS 8, you could do that. So it's going to go through that build process, like I said. And it does take some time, even on my my laptop with a solid state drive, but it's fairly quick. So once it's done building, it's actually going to spit out a whole bunch of other stuff about importing hidden imports, as well as then giving you the location of where the binary was dropped into, and usually that's dist, unless you for whatever reason change that. So let's go back into platforms, Linux. The other file, like I said, that was a requirement besides builds and requirement was your run.py. As you can see, this run.py is basically just kind of a wrapper around Salt to ensure that the commands are called properly when you call Salt from the binary, as well as give you the ability to interact with the Python shell within the binary, since Python is included. And then the pip shell or pip itself as well. I will tell you a caveat about pip right now. Pip installing with the binary only really becomes an issue if you are pip installing something that has a system requirement that wasn't present during the build of that binary. So say, for instance, you have a requirement on libcloud, and you don't have the system requirement that was required to be installed to build that package. Normally, it will fail with a rather confusing error when you try to pip install it into the binary, because it wasn't present during build time. So that system library was never brought in. There's also additionally the fact that since you didn't include that system package on the system where you were building, as well as pip install that package, it never had a chance to bring in that dependency. So just be aware of that. Okay, so we're still waiting for it to finish up the spec part of it. But yeah, your run.py could either be, say a simple script, or it could be something as like a wrapper, or it could be pretty complicated application yourself if you wanted it to be. But those are kind of the only 3 files required to do a Tiamat build. Tiamat itself does allow you to actually include additional files other than just those 3. as well as different means for installing pip requirements. You can either feed it a requirements file, or say you have a folder sitting locally where you downloaded all the wheel files already, or you have all the source code. You could tell Tiamat to point to that folder and use that for your dependencies if you so choose. Some people will choose to pin their binaries that way, or pin them in a requirements file. But it also allows you to include additional files as well. So say, for instance, you wanted to include service files or something like that, you could do so. We have actually chosen to include the service files via our FPM builds, which I will show you really quick. You can see here with our RPM make target, we go through the entirety of what we're doing via FPM. And effectively what we have right now is that we just build something called CPP salt. We drop it into the op folder and say, hey, we want to replace GD salt, which was sort of an alpha package of what we were doing, and then all of salt itself. And then our only dependency that we really have is zlib. It's the only non-common package that our binary actually has. However, zlib is pretty harmful on systems, or harmless, apologies. So it's something that was easy to include. And then we actually drop our config files as a part of that FPM install. And we have before and after install steps as well. All of this being fed by the variables set above. And those before install and after install will do things like stopping services, restarting services, enabling, so on and so forth. Okay, so the build is done. As you can see here, like I said, it says analyzing hidden imports, and this is actually, if you have it in debug mode, it's quite the wall of text to look through. But sometimes it is good to look through because, say, for instance, there is something you're expecting to be imported and you don't see it in this list, then you would probably need to go and ensure that you were installing the package correctly, or had the system packages available for that package to be installed. But as you can see here, the exe successfully built, and it was put into dist salt. So let's go down here, cd dist. And you can see salt there. Now this is going to be a shared binary. So right now it tells you it's an ELF 64-bit shared object. It's dynamically linked. You can go a step further, and in fact, we have played with this as well. You could use something like static X that then turn this into a static binary. Let's see if I have PyOxidizer installed. Okay, 1 second here. PyOxidizer analyze. I like PyOxidizer's analyze command the best for inspecting binaries. But as you can see here, we have a dependency for this binary on libc. That's installed pretty much on every Linux distribution out there. libdl, which is again just installed on almost every distribution out there as part of the core packages of the operating system. And then libc, which, like I said, isn't always installed on machines, hence why we have it included in our FPM. It also gives you some useful information about, the minimal glibc version that it's going to work on, and then minimal distro versions that you could use it across. Like I said, building it on CentOS 6 allows us to deploy this single binary to a whole host of distros and a whole host of versions of those distros. Granted, you don't have any concerns about security. So let's go ahead and get out of here and go back into Docker. Okay. So now we're going to run the make RPM command, and let's go ahead and cat the make file so I make sure I get the correct variables to pass in. Make RPM. CentOS 6. And then we need to set workspace again. Actually, let's just go up here. There we go. So we'll just make RPM. There are some other variables we need to set here as well, I believe. Workspace. Let's see about that. Install version. Maybe not. I might have fixed those up. Okay. All right, so yeah, let's try this, and I may get an error that I missed a variable somewhere, but we'll try it. So what this is supposed to do is actually run FPM from the root of the project, and it's going to find that binary in the dist folder. Build environment, that's what I missed. So let's go ahead and do that. We'll say prod. Oh, what did I do now? FPM filled parameters for upload credentials. Oh, I didn't set my creds, and I'm not going to do that on here. So anyways, what this does is it actually builds an RPM. And if we go over here, I'll actually show you what that looks like. We have our Yum repos where we've created one called CP Salt. You can see here we have one for each distro of CentOS we support, as well as each environment. So if we come into here, the latest package that was published today, which was 106. So these get uploaded at the end of that. And how that works via automation. Well, I suppose looking at it in the browser would probably be easier. How that works via automation is that make file is actually consumed by our Jenkins file, and here we set up a matrix to basically span our distros and our environments, and then we go ahead and set up our constraints for which things would build which things. So say, for instance, it's a branch, it builds dev. If it's a PR, it builds test. And if it's master, it builds prod. And then basically go through and we run those commands. So that CDs into Docker when the project is downloaded, and then runs the make binary. Same thing here, because we're using our credentials. And then we clean up. And that's it. The make RPM step actually is what is also doing the upload. So if we come back into the make file, sorry for jumping around. You can see at the bottom of this, we actually do a distro major version and then bin upload.sh. And all that really does is push things into our Yum repos. So that's how we build CPP Salt. Building the CPP template repos is far less interesting. The only thing you really have to show there is this is basically how everything laid out. This is the template repo for which every team gets cloned for them when they're onboarded into the core provisioning platform or Patchman. And those actually get cloned into a completely different org. So this would be my team's repo for this, as we dog food our own stuff. But we go into a completely different org. So we copy that template repo into here. And then the only thing that this contains, like I said, is a bin folder for some tools that we have around basically Salt. So there's a Salt CLI, but that's changing here so soon. Effectively, what it does is actually reach out to our ServiceNow instance and generates the inventory for Patchman, which is a patching automation platform we provide using Salt. It's effectively just a glorified formula with a bunch of extra modules, which I've written to facilitate internal tooling that is needed to be hit when you're patching servers and prod. But what it does is it generates the inventory from ServiceNow or CMDB and dumps that into an inventory file for us. Cloud just contains all of your cloud configs. Config, that's the configurations for master and minion. Salt, this actually contains a whole bunch of stuff. It's got your states, your reactors, pillars, orchestration, and anything else that people want to add in here, including our custom modules, which I've written. Yeah, so effectively all that happens when this gets uploaded is it hits the Jenkins file. And this was actually written by a teammate of mine, so all of his stuff is in the Jenkins file instead of a make file, but that's fine. But you can see here effectively what he's doing is kind of setting up the same scenario where we create our parameters for how to build things. And then it goes through stages where we do our get logic, basically to figure out which package needs to be built based on what files were built. And then we build those. So we build our minion RPM and our syndicate RPM, and effectively that's just FPM. It uses the same container that I created for FPM as well to build those. And then those are uploaded into the same location. And you can see here, there's the team minions and team syndicate packages for each one of the teams that are currently onboarded. And like I said, we have the rest of them coming on fairly quickly. So yeah, so all of that's provided. All the team has to do effectively is once they get their syndicate pairs is they can either use core provisioning platform, which is like a wrapper around Salt Cloud, to build their hosts, which will install their team package as well as CPP Salt, so the binary of Salt, and then they can just use it like normal Salt, with one caveat. If you're building Salt and you don't provide a run file that actually calls whatever service you're trying to run, Salt Master, Salt Minion, you won't be able to use the dash. So normally when you call Salt, say you want to use the Salt Minion or Salt Call or Salt Run, it's Salt Dash Run, Salt Dash Call, Salt Dash Minion, Salt Dash Master. If you're building from source, it's just Salt space and then the service or specific module you want to hit. So Salt Dash Key becomes Salt Space Key, and everything else. That's easily fixable. If you go and you look into the Salt Stack GitLab repositories, you can actually go to the Salt PKG repo they have, and it shows working run files, which make the dash a thing again. But it is something to be aware of. If you do build it from source and you don't include those run files, you will be really confused when things don't run when you try calling Salt Dash Master or something like that. So yeah, that's basically everything for those two packages. The only other thing I was really going to show was just really quickly, I'm going to pull request for the last one here. Oh. All right. So the last one built was, oh, we'll just go straight to there. Oh, God. I've come in here, coming to CPP Salt, we go to the master branch. You can actually see in the console log where it's doing basically the same thing. And like I explained with the Jenkins file, we use a build matrix to set up something for every distro and then every environment. It creates a separate folder for each one of those, as you can see. And since this is master, it's only going to build prod, so it skips dev and test. Clones the repo, and then it goes ahead and fires off the build for the binary. You can see here it's going through that script because we do a debug build just so we can capture everything. But you can see here that's where it starts printing out all of the environment. So it's doing the same exact thing you just saw locally, installing the necessary tools, installing the dependencies we have in the requirements file, analyzing everything, and then finally building there's a lot of it, so bear with me. Okay, we're almost there. There we go. Sorry. Once it gets done building everything, you can see it'll do a quick test via the Tiamat script we've written to make sure that the binary is actually callable and works. And then it moves into the FPM step, which you kind of saw. I'm just not going to enter my credentials in front of you. And you'll see that it then hits the upload script after it builds the RPM and it starts pushing it into our Yum repos. Boom. So that's effectively how we use Tiamat. Let me go ahead and turn the slideshow back up. And so you can see kind of the diagrams I provided before. Oh geez, it went all the way to the beginning. The diagrams I provided before, where this is a lot easier to maintain for us. And it's a lot easier for our consumers to digest as well, which is really important. because these are developers who are not people who have a lot of systems experience. So the easier we can make this to consume for them, the better. And the less things that technically will break. So next, upcoming Tiamat features. Okay, so one of the things that Tyler and I had been discussing for a while, and I'm just now getting time to get around to, and I hope to talk to Pedro about as well, is pluggable build backends. And effectively what that means is right now there's just PyInstall underneath the hood. However, there are a multitude of build tools out there for Python projects to turn into binaries. And each one has their pros and cons. So what we really want to do is provide a pluggable way of adding those backends so that you could say, hey, I want to use Tiamat, but I want to use PyOxidizer under the hood, or I want to use Nuicta or PyExe or what have you. You would be able to do that. It's all built using POP and the POP paradigm. So each one of these would just be plugins that are really easy to then integrate with into Tiamat. More comprehensive integration testing. Obviously, before this can come out of beta status, it really needs to be rock solid. It's not going to be a good situation if, say something isn't working and it's not captured by testing, and that ends up getting released to production. So more comprehensive testing will obviously be key there. And then Mac OS packaging. Actually, I'm sitting on a local branch where it uses FPM to actually build .pkg files. So once that's done, Tiamat will be able to build Wonder or one single package builds for Windows, Linux, and Mac. So we'll be covering the three big ones. I have not had any time to work on BSDs yet. So those are just a few of them. All right. Q&A. Oh, there's not much time. Oh,
That's okay.
chat.
Randy, this is David Murphy. I just want to point out, in addition to the platforms you talked about, Tiamat has already been working on platforms like Arista, Juniper, Solaris 10, 11, AIX.
Oh.
The Arista and Juniper, it's been working for over a year now. It's very subtly used in a major infrastructure.
So, we should get that added to the docs.
Yeah, it's on the
We
enterprise side at the moment.
should.
It's on the enterprise side at the moment, but the Arista is essentially CentOS 7
Right.
flavors.
Some of those are BSDs too, it sounds like.
The Juniper is essentially FreeBSD.
Yep.
Heavily restricted down in Junos. Solaris 10 and 11 are their own beasts, both for Intel and Spark.
Right.
And
Oh, Spark.
AIX is again PowerPC.
I want my Sparks back.
Really?
Not that back. Come on.
They just killed 11.3 and my M4000s.
Fair enough. But yeah, no. So that kind of answers that question. Tiamat builds successfully on a multitude of environments, and like I said, soon Mac. Just doing some cleaning up of that branch, and I'll get that pushed in as well. So it's a tool that can be used in several different places, and we definitely encourage you to use it. The more people that are using it, the more people have eyeballs on the code, the more contributions we get, the better. We definitely want to have this be something that's kind of driven by the community. So any interest in the project at all is definitely wanted. Any other questions? Sounds like no.
Sounds like a no. This is really great. Thank you so much, Randy.
All right. Well, thank you guys. I really appreciate you guys listening.
Thank you so much for joining us and sharing with us what you've got, because this is great.
Yep. And you'll notice that some of this was actually in my talk from the conference, but like I said, it didn't get uploaded. So I thought we'd step through that, then step through how we use it and how we have our build pipeline set up so that we can get that actually into YouTube.
Yes, we'll do it.
So I'm definitely excited for it. We've been using it extensively. And obviously the more people use it, the more the more we can basically shore up any shortcomings that it has to meet the requirements of our users.
Absolutely.
Yep.
Well, thank you, everybody. We're just a little over time. If there's not any more questions, though, we'll go ahead and adjourn, and I will make sure that this gets up on YouTube and gets sent out to people. And thank you for joining. Thanks for being here, everybody.
Thank you. Thanks, Randy.